Hello, good day to my dear students. Welcome for this video's another interesting discussion in science. For today's video, we are going to talk about the different image formations in spherical mirrors. So sit back, relax, and enjoy this moment of science with Mr. Rabino. In 3, 2, 1, intro! Mirrors are all around us. Char. Ito. um, Mirrors are all around us. We can't deny it, right? Because we use them, in fact, in our day-to-day experiences. Like when you take a shower, you always have to constantly look at yourself just to see if you look presentable or you look beautiful, you look handsome, right? So that's why mirrors have become an essential part of our daily tasks in life. That's why understanding their different image formations is also crucial for us to understand how light rays behave when they hit the mirror and use them for beneficial purposes. So for this lesson, we are going to focus on one type of mirror, which is what we call as spherical mirrors. So let me just switch to my PowerPoint presentation. So I'm currently looking for it right now. Let's see. Oops, sorry. Okay, where is it? Okay, there it goes. So let's talk about spherical mirrors. So when we speak of spherical mirrors, maybe you have actually seen them already. Like, of course, your sidecar mirrors, or maybe you have observed them in one of the convenience stores that you have visited, like the 7-Eleven. Oops, shout out to 7-Eleven. Baka naman. Okay, so spherical mirrors are a kind of mirror with a curved surface. And of course, just like plain mirrors, they utilize the reflection of light to form images. And that both inner and outer surface of the mirror can reflect light rays. So there are actually two types of spherical mirrors. Now, the other term for spherical mirrors are curved mirrors. So every time you hear curved mirrors and spherical mirrors, they are just equally the same. Okay? So let's talk about these two types of spherical mirrors. So spherical mirrors can be a convex and a concave. Now, when we speak of concave mirrors, it means that the reflecting surface of this mirror is on the inner portion of the mirror or the inner curve of the surface. And when convex mirrors, that is the reflecting portion of this mirror is on the outer curve of the surface. So that's how they actually differ. And it's because of these shapes of their reflectors that enables them to produce a variety of different image formations, which we will talk about later. So let's show a schematic diagram. So here is a distinction between a concave and convex mirror. So let's look at them, and you can see that the reflecting surface affects how light rays will behave when they bounce back to the source. So let's talk about more how we can actually describe the image formations in spherical mirrors. Now, one way that we can do to describe it is by the use of a ray diagram method, which we will talk about later. But let's discuss first about the characteristics of the images. Now, for concave, we call them as converging mirrors because light rays are converged when they reflect from this type of mirror. That's why they also are able to focus light rays. And image formed by this kind of mirror varies with the object's distance from the mirror. That means that if ever you're in front of the mirror, depending on the distance that you are in front of a concave mirror, your image characteristics actually vary or they differ. And of course, image can be small, they can be large, they can be real, or they can be virtual. We will unlock all these terms later on, okay? Now, let's focus on convex mirrors. For convex, They are called as diverging mirrors because they diverge light rays when it is reflected from the surface. And of course, image formed by this kind of mirror are always small and are always virtual, meaning to say it has the same orientation as that with the object standing in front of the mirror. So, image form is always smaller compared to the object. Now, I mentioned about ray diagram method a while ago. One of the ways that we can describe images that are formed in spherical mirrors is through ray diagram method. Now, in a ray diagram method, this is a technique that we can use that in order for us to describe one qualitatively, okay, the image formed by spherical mirrors. So, what does it show us? Now, the ray diagram method depicts how light rays reflect when they hit the mirror. And by analyzing where are these reflected rays are, or how these reflected rays are bounced back from the mirror, we can actually predict the characteristics of the images formed by concave or convex mirrors. So let's discuss about that right now. Now, in order for us to further our understanding, let's talk about first the parts of a spherical mirror. So we have here on the left side a diagram of a curved mirror. Now, each of these points that are reflected here in the diagram shows the corresponding parts of a spherical mirror. Now, to imagine this spherical mirror, I just want you to think of a circle, okay? Now, of course, a circle has a center, right? We call it as the center of the circle. Now, if we cut a portion of that circle, then we can think of it as a spherical mirror, okay? Now, let's focus on that one. Now, when you speak of the radius of curvature that is labeled as r in the diagram, that's the distance between the vertex and the center of curvature, okay, from C to B in the diagram. Now, how about the focal point? The focal point is the point at which reflected rays meet. And in most books, this is also called as the focus of your mirror. Meaning to say, this is where light rays meet when they reflect from the surface of your spherical mirror. And when we speak of focal length, that is 1/2 of the distance from the center of curvature. Now, if we are going to divide the center of curvature into two, the distance of that half the distance is your focal length. Okay, so that's it. Now let's talk about the other parts. We have the principal axis. Now, it's just an imaginary line from the center of the mirror. So, I mean to say, that line is not actually there, but we just assume that it's there just to serve as our reference point when we are going to have our ray diagram formation later. Okay? And of course, the vertex V is the center of your mirror. And of course, when we speak of center of curvature, that is the center of the sphere which the mirror forms a section. So how to understand this? Now, I told you a while ago that when we cut a portion of that circle, that is our spherical mirror. And assuming that that part of the circle is still complete, the center of curvature is actually the center of that circle, where we cut the section of our mirror. Okay? So, if you still don't get that, just rewind this video. Okay? So, let's focus right now on ray diagram formations. Now, when we describe images in the ray diagram, we just refer to this technique, which I will call as lost method. I am not the original author of that method, but I just found this on the books. So, we usually call it as the lost method. So, why is it called lost method? Because L stands for location. So, when we describe the location of the image, that is where the image is formed, and usually we use the reference points F and C in the diagram. So, What is F again? That is your focal point or your focus. And C here stands for your center of curvature. And let's move on to the next. O stands for orientation. When we speak of orientation, that's how your image will look like in reference to the object. So when you say inverted, that means the image is upside down. Meaning to say it has a different orientation from the object. For example, if the object is standing, then maybe your image is inverted or upside down. So, okay? In Bisaya, if nagbarog ka, ang imong image is nagbali or natuwad. Okay? Sorry for our English viewers out there. Okay. So, upright is erect image. So, that is erect, meaning to say it has the same orientation as that of your object. Meaning to say if the object is standing in front of the mirror or the spherical mirror, the object, or shall we say, the image has the same orientation as that of the object. Now, let's move on to the next one. S stands for the size, or we call it as the magnification of the mirror, or the image rather. When we say magnification, that's how big your image. Okay? Now, enlarged if it's bigger than the object, and of course, reduced if it's smaller than the object. Okay? And last but not the least, we forgot one thing. Equal, meaning to say the object size is just the same as that of the image size, meaning no change at all. Okay? Now, let's move on to the last letter, which is T, stands for the type of image. Now, when we speak of type of image, there can only be two types. It can be a real image, meaning to say it's an inverted image. Okay? And it is formed when light rays meet at a particular point after reflection from the mirror. Okay? And if virtual, it's an upright image, formed when the light rays appear to meet at a definite point after reflection from the mirror. So, how do you describe an image if it's real or virtual? Just very simple. If the image appears inverted, then that is a real image. Okay? And if the image that you see appears to be upright or has the same orientation as that of the object, then we can say that the image is virtual. Okay? So, that's how we describe images in this case. Now, let's focus on ray diagram application. But first, let's do it for concave mirrors. We use 3 rules in applying ray diagram construction in this case. Now, let's look at these rules one by one, and let's check how each rule can be applied when you construct your ray diagram method. So, let's look at first rule number 1. Light rays leave the object upward, arrow in the diagram, parallel to the principal axis, which is your P, are reflected and passed through the focus or your focal point, which is the big letter F. So how do you apply this one? It's just simply as like this. First, you draw from the tip of your arrow, which is the object, a parallel line to the principal axis, which is the imaginary line from the center of the circle or the P. Okay? You draw a straight line until you reach the surface of the mirror, and then once it reaches the surface of the mirror, it is now reflected. So it is now being shown as the dashed line here, or the dashed arrow, and we have to let it pass through the focus or the focal point. Okay? So this is how you interpret rule number 1. Okay? Now let's move on to the second rule. For the second rule, light rays that pass through F are reflected parallel to the principal axis. So how are you going to construct this? Simply as this one. First, from the tip of the arrow or your object, you just draw a straight line that passes through the focus. And of course, you always let it reach the surface of your mirror. Okay? So as it passes through the focus and reaches the surface of the mirror, it is reflected parallel to the principal axis, which is your P in your diagram. So that's how we are going to interpret this second rule. Okay? Now, let's move on to the third rule. The third rule is any light rays that passes through the vertex or the V, that's the center of your mirror, will strike the mirror at the same angle as the incident ray. This is actually the law of reflection, in which the angle of incidence is always equal to the angle of reflection. So if you do that, it's like this. It hits the vertex of the mirror, and you always reflect it back with the same angle as that of the incident ray. Where do you measure the angle from there? Just measure the angle in reference to your principal axis. So when I constructed this ray diagram, I assume that the ray diagram is already at an equal angle from the incident ray to the reflected ray. So this is how rule number 3 is applied. Now, if we are going to merge all these 3 rules, it's like this. So that's rule number 1 a while ago. That's rule number 2. And then this is rule number 3. Where all the light rays meet, where all the reflected rays meet, that is where the image is formed, as indicated from my blue arrow. Okay? Now, why is it inverted, sir? You might ask, right? Why is the arrow inverted? It's because, look at your principal axis. The intersection of the 3 reflected rays from the 3 rules that we discussed a while ago happened below the principal axis relative to our object, right? So that's why in this case our arrow is inverted, because the intersection happened below the principal axis in reference to our object. So that's why the image there has a different orientation from our object. So that is how the image is formed in this case for concave mirrors. And the image description, so let's use the lost method here. The location is, if you look at the location of the object, or the image rather, the blue arrow, it's somewhere in between the point F and point C, right? That's your L. Now, what is the orientation? Okay, the orientation, take note of the blue arrow. The blue arrow has a different orientation from the object. So that means that the object and the image have a different orientation, which indicates that the image must be inverted. Okay? Now, its size. How about its size? Just look at the relative size of the arrow. If I just have a ruler right now, I could definitely measure that the image in this case is actually reduced, or meaning to say it's smaller than the object. And of course, what type of image is formed? It's a real image. It's because, as what I've said a while ago, if the object, or the image rather, is inverted, then that also follows that the image type is a real image. Okay? So that's the image formation for concave mirrors. Now, for concave mirrors, in addition, by the way, the image description varies with the object position in front of the mirror. So we will talk about that later. Now, let's focus first on the ray diagram for convex mirrors. Now, for convex mirrors, actually the same rules are applied, but it's just that it will have a different interpretation when we perform it in our diagram later. So for rule number 1, it's just the same. Parallel rays of light from the object, which is the upward arrow, are reflected, so they appear to come from F behind the mirror. Now, in this case, center of curvature as well as the focus are found on the other side of the mirror, because we are now talking about convex. Okay, so how do you apply this? Just draw a straight arrow parallel to the principal axis and hitting the surface of the mirror, and you let it be reflected so that it passes through the focus of the mirror from the other side. Okay, so this is how you apply rule number 1. Now for rule number 2, a ray directed towards the focal point is reflected parallel to the principal axis. Actually, it's just the same as what we did in concave mirrors. So what are you going to do in this case? Is that you draw a straight arrow which which passes towards the focus on the other side of the mirror, and depending on where the arrow has hit the surface of your convex mirror, that is also the point where you are going to reflect the rays parallel to the principal axis. Okay, so this is now rule number 2. Okay, now for rule number 3, it's just the same. Light rays pass through the vertex is reflected at the same angle as the incident ray, which is of course the law of reflection in this case. So assuming that we did it carefully, that is assuming that it has the same angle from the incident ray, and the reflected ray also has the same angle as that of the incident ray. Okay, now let's combine those 3 rules a while ago. Now, ray diagram for convex mirrors, it now looks like this. Okay, that's rule number 1, and this is rule number 2 a while ago, and this is now rule number 3. Now, where are all these intersections happening? Yes, you are actually right. It's happening on the other side of the mirror. Now, in this case, I indicate that one with an upward arrow, because you can see it's where all the intersections are happening. But why an upward arrow, sir? It's because relative to the position of the object, it's located above the principal axis, right? And we can also see that the reflected rays depicted by the dashed lines are also happening above the principal axis. So that's why we draw an upward arrow, and that is now where the image is formed. Now, how do we describe this image using the lost method? So location is behind the mirror because it's located on the other side, right? And upright, why did I know that it's upright? Because it has the same orientation as that of the object. That's why it's upright. And how did I know it's reduced? Look at the sizes of the arrow. The image is relatively smaller compared to the object. And how do I know that it's virtual? It's because every image that is an upright one is always considered as a virtual image. And this is how you are going to describe images that are formed in convex mirrors. And for convex mirrors, the description of the image is always the same. Wherever you place the object in front of a convex mirror, the image characteristics just does not change. It's always behind the mirror. It will always be upright. It will always be reduced or smaller than the object, and it will always be virtual. Okay? Now, how do we apply this? For convex mirrors, usually we apply them in rear view mirror of the vehicles. Maybe you have seen them, no? If you have some cars over there, right? And of course, no, shop security mirrors, especially in convenience stores, no? And of course, blind curve mirrors are also a convex type. Now, they usually use this kind of mirror in order to give a wide view of the object or the image that they are viewing. So in the case for convenience stores, convex mirrors are really very essential in terms of security, because when you look at yourself in front of a convex mirror, you will always appear smaller, so the scope of the image is eventually very wide. Okay, So that's why convex mirrors are typically applied in this scenario. Now, how about for concave mirrors? The headlights of your cars are actually composed of concave mirrors. And in order for us to know what's the use of that one, it's actually to amplify the light rays, no, from your bulbs of your car. No? As you can see there, that's actually a dentist mirror. Yes, that is actually a concave because you need to magnify the object or the image, no, of your tooth in order for the dentist to see it clearly. And of course, for telescopes, we call it generally as reflecting telescopes. Okay, so they are actually used in telescopes for astronomical observation. So those are just some of the common uses of these types of mirrors. Now, in order for us to somewhat appreciate the image formations, no, you don't actually need to perform anymore the ray diagram because there are a lot of applications available on the net. Like for example, I want to show you what I found on the net. So it's this. Okay. So let's use this application right now I found on the net. So this is from physicsclassroom.com. So Physics Classroom, shout out to you. Thank you for providing us with the wonderful simulations for this activity. So we just need to click on this and it will change to mirror. Now this is actually a concave mirror on the left portion of the mirror. So as you can see, this is a concave mirror. By the way, 2F here is the center of curvature of your mirror, while F here is your focal point or your focus. Now as you can see, I can actually make the height bigger so that you can see clearly. Okay, let's do that. Now as you can see here, let's say if I place this here, you will see that the image is inverted. Now let's look at the size here. The size actually here is in terms of the height. Now for the object height, that is set for 26.5 centimeters, and now the image height is only negative 12.4 centimeters. So technically, the image here is smaller compared to the object in terms of height. Okay. Now you might be wondering, why is it negative, sir? Now a negative sign there indicates that your image is inverted, or meaning to say that the image has a different orientation from your object. Okay. Now what do you think will happen as I slide this across our screen? So as you see, as I slide it across our screen there, let's slide it over there. Okay, let's put it exactly at 2F. You look at the size, it's almost roughly the same, 26.5 centimeters, and the image height is 26.4 centimeters. Let's just consider it as the same, no? So if you place it at 2F, it becomes the same height, no, as that of the object. Now let's drag the object so that it will be between the 2F and F of your mirror here, there. So as you can see, the image here gets enormously bigger than the object, right? So the height of the object here is just 26.5, but the image height is now negative 54.6 centimeters. Again, don't be confused if there's a negative sign. The negative sign there just indicates that the size of the image, or the orientation of the image rather, is inverted or different from that of the object. So now what if I slide this F? If you slide this at F, you can't see the image here, right? So that's why we always consider, if the object is always at F, the image is actually cannot be seen. So if you look at yourself in front of the concave mirror in this case, so you will see a blurry image of yourself from the concave mirror. Now if you place the mirror exactly in front of F, you will see that our image is actually very big, but at the same time it's already in behind the mirror. But if you look at the orientation of the image, now you look at the image, it's now positive. The positive sign of the image height here means that our image has the same orientation as that of the object. Okay? So in this case, this is now a virtual image and at the same time an upright image, but it's bigger. Okay? Now, of course, if we continue to do that one, you can see a play of the image formations in concave mirrors. Now, how about for convex mirrors? Just for convex mirrors, all you need to do is just drag this one in our other side of the mirror. And as you can see, wherever I drag this object in front of a convex mirror, the image is always relatively smaller compared to the object. But of course, look at this. As you approach the mirror, you tend to be getting bigger, but not bigger than the object. Now, in case here, as you go nearer to the mirror, you also become bigger and smaller at the same time. So that's why concave mirrors have varying image formations for our scenarios. Okay, so let me switch back and return to my PowerPoint slide to continue our discussion. And of course, for concave mirrors, this is what will be your activity for our asynchronous encounter later. So for concave mirrors, we have different positions of images. We have object beyond C, object between F and C, object at C, object at F, and object in front of F. So this is just the link that we just visited a while ago. So if you want to observe what happens to the image characteristics of these objects placed in different positions, you may visit the link that is given to you right now. Okay? And of course, don't forget, in connection to this activity, to answer your asynchronous activity in our learning environment or in our virtual learning environment. Okay? So these are the illustrations for each case. That's scenario number 1, scenario number 2, scenario number 3, scenario number 4, and scenario number 5. Okay? Now, for case 1, object beyond C, this is how it looks like. The description is between F and C, inverted, reduced, and real. Okay? Now, for case 2, object at C, the description is the object or the image is also at C or at center curvature. It's always inverted, but the same size as the object, and it's a real image. And for case 3, object between F and C, the image now is beyond the center curvature or C. It's inverted still. I'm sorry, it's enlarged because it gets bigger, and it's still a real image. Now, for object that is at the focus or at the focal point, no image form. Okay? Now, for case number 5, object in front of F, there. It's behind the mirror or located on the other side of the mirror, upright, enlarged, and they are virtual. Okay? So I hope that helps. You can verify this by visiting our virtual laboratory or simulation that we had just a while ago. Okay? So to summarize everything, there are different kinds of mirrors. Each of these kinds of mirrors has different image characteristics depending on where the object is placed in front of the mirror. While convex mirrors always produce virtual, upright, and reduced image size. And for concave mirrors, they always produce either real or virtual, upright or inverted, or enlarged or reduced depending on where the object is placed in front of the mirror. And depending on the image form, these mirrors are used in various situations, making it one of the essential tools that we can have in our society. And that completely ends our discussion for this encounter. To summarize everything, there are two kinds of mirrors, concave and convex. And each of these kinds of spherical mirrors have different image characteristics depending on where the the object is placed in front of it. So, In order for us to learn more about concave and convex mirrors, let us appreciate what else? Let us acknowledge the fact that without these mirrors in our daily life, we might not be able to enjoy things the way they are right now, right? So in our next video, we are going to talk about another kind of technique that we can use in order to describe the different image formations in concave and convex mirrors, and that will be through quantitative analysis through the use of mirror equation and magnification equation. That will be the next focus of our video. So this time, let's end this video because we have been talking a lot already. Thank you so much for staying tuned with our discussion for this video. So I hope that you have learned something from this very short lesson that we just had for this video. So thank you, God bless, and I hope that you had a great time. Keep on learning, and of course, most of all, enjoy learning science. Bye everyone. See you once again next time.